After reviewing the option list, we want to explain more about the details.
Now we want to have more explanation uh, about the options that we can put inside the function of the simulated annealing options. The first one is max iteration and max fun evaluations. Define 500 and 5000 times. The first one is a stop if the algorithm reaches 500 iterations, and the second one is a stop if the objective function is evaluated 5000 times. Max iteration and the max function evaluations are two independent stopping limits, but they are related through the number of objective function evaluations performed per iteration. We can say the maximum function evaluations is estimated by multiplying evaluations per iteration by the total number of iteration. Generally, it means that it is approximately equal to 1 per iteration. So, what is the reason that sometimes we have more evaluation inside the algorithm? We have three reasons for the higher number of iterations there, and these are re-annealing, constraint checks, and the initialization steps that could make that the function evaluation number is getting a higher number if we want to compare with the iteration. The other option is initial temperature. It is 10, and we set the starting temperature, and we know that if it is high enough, it means that we have more random exploration at the earliest stage. In simulated annealing, the temperature controls how easily the algorithm accepts worse solutions during the search. A higher temperature allows more random exploration. A lower temperature makes the search more conservative. Uh, the initial temperature depends mainly on the scale of the objective function. But just as an example, here if you pay attention to the table, if we suppose that 20 creates a very random early search during the process of the optimization, then we can guess that, for example, 10 would be a good exploration number. So 5 would be a kind of moderate exploration number for that algorithm. And then we can expect that one is very greedy search number when we adjust the initial temperature option of the SA algorithm. The next option is the temperature function, and temperature function computes the new temperature at each iteration based on the initial temperature and the iteration number. Uh, Here we can see the temperature function is adjusted at sign temperature exp. Um, this specific temperature function is used as an exponential cooling schedule to reduce the temperature over time. So for example, here we can see that MATLAB can update the temperature approximately as Tk equal T0 multiplied by alpha to the power of k. In this equation, we have T0 initial temperature, k iteration number, alpha the decay factor would be less than 1. And the meaning of this expression is that the temperature decreases exponentially as iterations increase. Here we can see different temperature functions, temperature exp, temperature fast, and temperature bolts. The temperature function here controls how fast randomness decreases through the algorithm. If you want to compare the different functions, we can say the Boltzmann or the temperature bolts has a slow cooling procedure, maintains the exploration longer, and we can say it is good for complex and highly non-convex problems when we have many local minima in the optimization problem. And we have another temperature function. It is fast, and it means we will have very rapid cooling with selecting this option. It focuses on local search, and the temperature fast would be useful when the problem is relatively simple or when we need faster results, so we can accept a higher risk of getting trapped into local minima. So for different problems, we can select one among these list for the temperature function. And on the top, you can see a typical temperature evolution. If we consider the initial temperature is 10, how the temperature decreases by the temperature function. As I mentioned before, the temperature function controls how fast this reduction happens, and then after that how fast randomness decreases. It is something that the temperature function is doing. We have an explanation here about the original simulated annealing and what we have in MATLAB. The original simulated annealing theory mainly defines three components. First is a state generation. It means how a new candidate solution is generated. Then second is acceptance rule or metropolis criterion as an example or as a criterion. Then we have cooling schedule, and it means how temperature decreases and how we can control the randomness. So in the classical theory of simulated annealing, there is no parameter called re-annealing interval, the things that we have in MATLAB. So for the re-annealing, for example, here adjusted 100, we can say that it specifies after how many iterations MATLAB performs re-annealing, which means it rescales the search step sizes based on variable sensitivities. What does it mean? It means every 100 iterations, the algorithm reevaluates how sensitive the objective function is to each variable. It then adjusts the step sizes for each variable accordingly. And what is the reason uh, uh, for being useful adjusting this parameter? During optimization, some variables affect the objective more strongly and others have little influence. So re-annealing, the thing that re-annealing do is that increase the step size for insensitive variables and decreases step size for sensitive variables. It is what re-annealing do, for example, for this specific case, after 100 iterations. To the reannealing option, we can add these explanations. Reannealing is a practical improvement used in engineering implementations, not part of the original simulated annealing theory. It was introduced later in adaptive simulated annealing method, or ASA. The idea is to periodically rescale the search step sizes based on variable sensitivities. So, conceptually, measure how sensitive the objective function is to each variable. 2. Adjust the step sizes accordingly. 3. Continue the search with better scaling. And these things prevent the problem, such as it is the profits that bring with this adaptive simulated annealing variables with very different scales, inefficient exploration of the search space. So these are the things that are prevented when we use the adaptive one. So here we have a table. We have different concept: temperature, cooling schedule, metropolis acceptance, reannealing, adaptive step scaling. We can see that the third one for the classical SA theory is yes, 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 and the reannealing and adaptive step scaling is no. These are the capabilities and the features that have been added to the adaptive simulated annealing, which we have as a function inside the MATLAB software. The other option, annealing function, we have. For annealing function, we have three options: annealing bolts, annealing fast, annealing bounds. We can see in the table the behavior and the typical use. For the annealing bolts, we have Gaussian step, Boltzmann distribution for the faster exploration, and for the bounds, the behavior is respects variable bound carefully. So for the typical use, the annealing bolts general continuous problems. For annealing, the annealing fast option is used for large search spaces, and annealing bounds is good for constraint problems. And with the annealing function, we can check how new candidate points are generated from the current solution. On the other table, we can see the difference between the annealing function and the reannealing interval. What is the difference in role and effect they have? We can see that the annealing function is used for generating new candidate points, and the effect is controls exploration pattern. But the reannealing interval is used for rescaling variable step sizes, and the impact is improving efficiency during search process. In this slide, we can see one of the annealing function, the annealing bolts, and we can see in this formulation how the new x value depends on the current x value, and also how depends on the temperature, and also a normal random variable n01. And this is how the annealing bolts relate the x new and x current. In summary, about the simulated annealing in MATLAB, we can say SA is a global optimization algorithm inspired by the cooling of metals. It balances exploration for high temperature and exploitation for low temperature to avoid local minima. The algorithm accepts better solutions and may temporarily accept worse ones based on a probability criterion. MATLAB solver, the simul anil BND, is easy to implement, just require objective function and variable bounds. The performance depends on temperature schedule, stopping criteria, and algorithm options. Best suited for nonlinear, non-convex, and derivative-free optimization problems, where traditional methods may fail. And while computationally slower than gradient-based methods, it is robust for finding near global optimal solutions. Thank you for your attention.